everyone, and welcome back to the Information Bottleneck podcast. And today we have Rao Kambhampati. He's a professor at Arizona State University. Hey,
Hi.
nice to have you. Thank you for coming. And as always, ALM.
Nice to see you again, Ravid, and nice to meet you, Subararo.
Rao.
Yes, nice to meet you, and can't wait to.
For the rest of the thing, you can just call me Rao. That might be easier. But full name is Rao Kambhampati, but most people call me Rao.
Yeah. Well, happy to chat about reasoning models.
Yeah. So today we are going to talk about reasoning models. I'm sure that all of you already know what does it mean, reasoning model. But I think we will start to go a bit deeper in what does it mean, what are their benefits, why they work, when they fail, what we can learn about them. So yeah, maybe we'll start with a bit background or like maybe with definition. What do you call reasoning model?
So the interesting part, of course, is reasoning. Giving a very precise definition for reasoning has been an issue. People tend to give examples of problems and specific ways of solving them that would correspond to reasoning, logical reasoning, for example. And in my own work, I considered generation of plans, which is coming up with a sequence of actions or a course of actions to go from a particular initial state of affairs to some desirable state of affairs. It's a sort of a reasoning problem. It involves temporal reasoning, reasoning about actions, reasoning about resources. And my own background has, way before these LLMs, my own background has been in planning and decision making. And so when, back in 2023 timeframe, basically ChatGPT, even before that, when GPT-3 became very popular, we started seeing all this stuff about the LLMs are already able to do planning and reasoning. There were already several papers saying, in fact, I joke that for a while, and maybe it's continuing now, but for a while, the most popular title for a NeurIPS paper or an ICLR paper is LLMs are zero shot XXX, where you throw in whatever you want in the XXX. And so there were several about planning, and that didn't make too much sense to me, knowing what is generally involved in planning. And also as you know, from like the whole Kahneman style view of system one, system two, typically the planning, reasoning tend to be sort of, especially planning tends to be associated with deliberative system two. And it looked to me that the way we are training LLMs, despite the fact that we don't have a clean-cut understanding of exactly what is happening in the 17th layer in the activations. The way we are training the LLMs, they are like massive system ones for the humanity. And so they can essentially kind of get you things that are close to the training data, but they may not be able to put plans together. We have shown that was actually the case, that even for very simple toy problems like stacking blocks on top of each other such that they're in a certain configuration, sending stuff from one place to other over trucks, and also going all the way to even other slightly more complex toy problem like Sokoban, where Sokoban is a great example of a planning scenario where basically you can't reverse your actions. Those of you may not remember Sokoban, it's essentially you get to push boxes into a certain configuration. You don't have the strength to pull, but you can only push. And because of which, if you push them and you need to push them into a certain configuration. So if you push, some intermediate configuration that is wrong, you can't undo it. You're basically stuck. And that's a classic example of what makes planning hard to begin with, non-ergodicity of the world. That is, when the agent is acting in the world, if it gets into a state from which it can't come out, it can't reach other states, then basically planning is hard. And so we showed that pretty much Blocksworld actually is much simpler. In fact, you can blunder your way through Blocksworld, whereas in Sokoban you can't. And we showed at that time that standard LLMs actually don't do well in any of these things. This was 2023. There were like 3 papers in NeurIPS at that time talking about PlanBench and the limitations of the LLMs, etc., on planning. Now, 2024, basically, it's around September, I think, actually, we had the first of the quote-unquote reasoning systems. O1 came along, the strawberry came along. Before we talk about reasoning systems, let's also mention that up until O1, we pretty much knew there were papers about how things were trained. Right. Like GPT-3, there was a paper. It won the best paper award in Europe. We knew pretty much everything that they did. They basically had like, a 40-page, the appendix, etc. But then that changed slowly. And, a classic a cleavage point was had to wait pretty much until January of 2025 when DeepSeek came along to know that this is how here's a system that actually does pretty much as at the same level as O1 style system, O1 to O3 style level systems, and you know exactly what they're doing. I mean, we still don't know how actually OpenAI trained their system. We definitely don't know how Gemini trained their system, and certainly nobody knows what happens in the Grok in terms of the post-training part. So the phrase post-training became popular, and we didn't quite know what was happening. There were like guesses. But now we have a pretty clear picture. If you assume R1 was a good example, then in essence, the way to think about essentially is before this itself, we kind of knew that if LLMs are trying to guess a plan, they're likely to be incorrect. And then you will actually try to execute it and you'll find it to be wrong. But if you have a verifier of sorts, and the verifiers can come either because of classical verifiers for problems, you can learn verifiers, you can also have LLMs themselves to develop verifiers, in a sort of a recursive framework. If you have these verifiers, you can do generate test with the LLMs. And the good things about LLMs is unlike infinite monkeys typing Shakespeare, they are much better as generators. They are not giving guarantees that what they generate is correct, but they're more likely to generate stuff that's likely to be plausibly close to something, close to a plan. And so then if you have the verifier kind of say, no, try again, that essentially would be equivalent to something like simple generate test. And you can also have the verifier actually give an criticism as to here are the problems where here is the parts where the plan is incorrect, and you can actually do that as a back prompt, and that changes the next candidate generated. Called this, we actually came up with this thing, and I had published it in ICML 2024, and we called it LLM-Modulo external verifiers. Now, if you think of what R1 is doing, you can think of it as taking the verifier, putting it into the post-training stage. So instead of waiting for like a user to give you a problem, you generate large number of synthetic problems. LLM guesses solutions. In the case of R1, it guesses like 15 or so solutions. And verifier checks if any of these solutions are correct. If so, then essentially you can use that as a signal to train the generator so that it becomes over time better at generating more likely correct plans. And this training can be done in all sorts of ways. SFT is the normal way people used to do it. And then DeepSeek R1 made this RL training to be the bigger catchy thing. But if you think about it this way, then you kind of realize that what is happening is previously we had only had the declarative data. If there are plans that were present in the training data, this can be used to fine-tune the LLM, train the LLM. But there are not enough plans in a certain area, enough example in a certain area. You can generate synthetic data, check if it is correct or not with this verifier. Verifier is sort of coming again from the humanities knowledge. These are, a lot of this could actually be procedural knowledge from the humanity, unlike declarative knowledge. And you're using this procedural knowledge to actually train the LLM correctly. So one of the funny things is even before this, LLMs can blurt out procedures, but they don't know how to use them. It was very well known for a long time that they can just give you the code or the pseudocode for a procedure, but not necessarily know that the plan that they generated is actually wrong by that procedure. And so we were actually putting this in our R1.
But do you think this is at the end, like you describe a mechanism, right? Like let's do RL on the top of the pre-trained model. But do you think this is like essential to planning or like to what we call reasoning? Because yeah, like we have this mechanism and it become better in a lot of different tasks and different benchmarks, right? But do you think this is actually like related to planning and reasoning?
No, so here's the idea that one way of doing planning is to, I mean, there was this way before all of this, there were these areas like case based planning, which essentially said, you don't start from scratch anytime, just have all plans in the memory and then try to modify them on demand. It's not exactly, that's not exactly what LLMs are doing, but there is some connections between essentially trying to actually show reasoning behavior, like generate likely correct plans with respect to this but then the point of course is how are you training it such that they're actually correct. During the training stage there is a teacher, there's a verifier which is telling you which is right or wrong. Testing stage there is no teacher. So in fact one of the things we did when O3 O1 came along is we showed, for example, that O1 can still be wrong, obviously, during the inference stage, and that if you put a verifier for in the test time scaling, its accuracy improves with guarantees. So what is really happening is you're improving the generator from infinite monkeys to GPT 3.5 to O1, O2, O3, which is great progress. But if in fact if there is somebody in the loop, if these things are sort of helping humans, this is no problem. If on the other hand, you're actually doing this plan, for example, in the world, which is what is happening in the agentic systems, no wonder why every once in a while there is actually, actual non-ergodic scenarios, such as you delete all the mails, you can't bring the mails back. And that's what this poor Meta woman found, right? Every once in a while, you will see that essentially the plans that it actually just goes ahead and executes can actually get you into trouble because there is no verifier in the loop at that time. But most of the other plans seem to be working fine for two different reasons. One because probably the generator became better. Second, because probably there were no interactions between the actions. So you are playing in environments that are actually quite ergodic. And that's a great way of stabilizing the world. I mean, for example, when we have kids, we make sure that the living rooms are ergodic, right? We don't actually put big, dangerous things in the room and see if the junior can deal with it. And that's a reasonable thing. And so when, in fact, you have
You should tell it to my kids.
so, so if you have those sorts of domain. So, for example, by the way, PlanBench, which has become like a sort of like a poster child for a certain kind of agentic reasoning systems. Other you're spending time trying to figure out, okay, tell me, where are all the places where they have interactions between actions? Because if that's how you start having, difficulty in planning, they actually make sure that there are no interaction between actions. So you make a benchmark where essentially all you are trying to do is pick the actions and pretty much put them in any order. It will more or less, for sub goals, that will more or less work. And that's, basically where we currently are. So that's why once in a while, when there is actually non-ergodic world outside, you try it out, then, then basically you can have problems, in terms of actually they're removing your directory and you don't have a backup, for example.
But do you think like the solution, right? Like let's assume that a good solution for like one model in isolated world is like RL post training. Do you think the solution when we move to world of agents? Do you think this solution is still good enough?
I think it depends on. So there are two issues, right? One, it's you hit the nail on the head in a certain way, which is the question is if you're training them, on certain population of problems, how much generalization is likely to happen? The whole out of distribution generalization, which has been the, bugaboo of machine learning forever, right? So the interesting question is there's very little we know about out of distribution generalization. First of all, they never learned the algorithm, even for very simple things like last data concatenation. The way you do the post training, it's essentially training itself to overfit to longer and longer unrollings of the algorithm. But having said that, if the part of the issue, in fact, I think somebody else from one of these companies was saying that the frontier models tell you everything except the one thing that matters, which is what's the training data, what's the post-training data. And if you know that, you can actually have a sense of how much generalization is happening. And if there is enough generalization, this could be a computationally efficient thing. Imagine you sort of trained on, let's say, for a very simplistic way of thinking, you trained on a bunch of Blocksworld problems, and suddenly it starts doing much better on logistics, Sokoban, etc. That's great. That is basically what I want to see. But there is very little um, convincing support for that, because all we have is when people do it on, like, basically they start, let's say, like a pre-trained model, a small pre-trained model. Even with a small pre-trained model, it's a tricky issue because you don't know what the pre-training data was. And then if you actually just fine tune with certain types of problems, normally they show that if you fine tune with 3 to 5 Blocksworld problems, it's able to do 7 to 8 block stacking problems, for example. That's a kind of generalization, but not exactly the kind of generalization that people might have in mind when they say to make this actually worth the cost. So right now, there one of two both possibility, the two possibilities, both of which can be true, and I don't know which one is. One is we are training these essentially as Rube Goldberg machines. I hope you know what Rube Goldberg machine is. And so these are highly inefficient ways of training. And people already know that LLMs are not trained the way, quote unquote, humans.
Well, let's describe, like, let's explain people what does it mean, like a
So a Rube Goldberg machine essentially is a machine. I mean, this is actually Rube Goldberg this is a competition. I think it still is happening, an annual competition in Purdue University. And long back, there was this guy, Goldberg, who apparently started this. The idea was to come up with a ridiculously complicated mechanism to do something very simple. And my classic, I mean, there are many jokes about this. There are actually, if you go to Wikipedia, they show some of these things which are ridiculous. This seems like an overly complicated and probably almost non-minimal solution to what you're trying to do. And that's basically what Rube Goldberg machines are. And so the question with LLMs, when I'm saying this, I'm not exactly, I mean, it's just sort of an analogy that you could well be essentially training them with so many different kinds of data, and it's going maybe epsilon away from the training data. And that's pretty good for you because somebody else has already trained and whole bunch of us are using it. So if the amortization costs might be working fine and we could be happy with that, that's one possibility. The other actually is they're actually not training with that much different types of data. They're only training with few types of synthetic data, and it somehow is able to generate solutions even outside, or at least get good guesses even outside of the domains it's been trained on. In normal science, we would know the answer to this, but AI is no longer normal science. Science is about understanding nature's secrets, and as I say, AI has become understanding OpenAI and Google's secrets as to what they are doing, because they know what they're doing, and we just don't know, and we only have the contraption, the model. But it's obviously useful, given that somebody has already paid for it and they did the training. It is clearly the case that, we have these coding models, we have these, math models, they're all kind of useful.
But do you think does it matter at the end? Yeah, I understand that we have this aspect of trying to understand and to make actual science and things like that. But in practice, does it matter if these models are generalized to other domains? If we just give them if they answer all of the important questions or on the important fields that we care about?
That's fine with me. That's my point. So they are not. So I am one of those people who is not very much behind LLM should be ignored because they are not the way humans do things, because AI has done this before, and in general, and of course in engineering too. Obviously, if we waited for the first flapping wing planes, we would not be traveling anywhere, right? Because we had to look for very different kinds of designs. I basically think of these as great intelligence enhancers, and they are trained in a very bad, it could be very unlike how humans might be trained, that's completely fine. I'm with you that as long as the economics works out, right? In the sense, the amount that you're pouring. Because the thing that I talk about to students typically is this thing in computer science about amortization cost. We all know that if you have a graph, and if you give a start and a goal node, you can do a star search and find the optimal path. But we also know that we could actually have solved all pair shortest path algorithm on the graph. And then once you've done that, then basically you have memorized all the optimal paths, and then whichever S and G comes, you can just give the answer right away. Most of the time, it's clear as to whether it's worth doing all pairs shortest path or not, because if somebody is asking just one question, doing that is too costly, and the time you spent would not be made up. But Google, I'm sure Google Maps does that because they know that there are enough people who ask random start goal pairs, and so they pretty much do some sort of a all pair shortest path in the hierarchical level, higher level, and that sort of amortizes over the use. So it's economics that matter. Right now we don't quite know whether economics are mattering because they really matter, whether they're actually balancing, or it's because we're in a nice bubble. That we don't know.
So we just need to be on the right side of the bubble. But do you think like the solution, like now, if you need to pick like one direction to work on, like, or OpenAI needs to pick one direction, do you think the solution will be like, I don't know, betting on cheaper GPUs, or like smaller models, or like we need to better learning algorithm, or maybe other architecture designs?
I think basically it's very clear what they're doing, right? Essentially, we have, like Sarah Hooker talks about hardware lottery. LLMs of transformers have won the software lottery, right? And, you can have people, like including Jan trying until cows come home, saying we should look at other architectures. But all these people have spent way too much far on these architectures. This is there. There's a beautiful essay by Dilip George about how dirigibles, basically were the only thing that was going on. Nobody was working on fixed wing airplanes for the longest time. And when people hear about the Hindenburg, they only remember the disaster. They forget the fact that before that, people were using that to go between US and Europe. That was the technology that was working. And so at that time, people will talk about how to paint dirigibles better, etc., etc. And you would not have known that this technology will stop at some point of time, some other technology comes. And so companies, obviously are not going to be able to have the luxury of trying out completely different architectures. They're mostly trying how to improve the training, how to improve the inference cost. Currently, that's like one of the other things. And interestingly, that inference cost thing too, weirdly enough, is you overtrain to reduce the inference cost. That's basically what happens, because what people tend to think of intermediate tokens, we could talk about that, but intermediate tokens have become like this thing that have got synonymous with reasoning models. Previous, models will basically you prompt and they'll give completion, and pretty much the whole thing is considered the solution. Now there is think begin, think end, solution begin, solution end. And people basically realize that the longer the think trace is, they try to say that must mean it is thinking too much. There's a lot of work being done. Use the thinking to reduce the efficiency. It's one of the strangest things that happened, mostly because Altman started charging people with O1 time and O1, O2, O3 time frame for these intermediate tokens, saying we won't show you those tokens, but you still have to pay for them, right? And so, of course, with R1, we actually know what tokens are being generated, and people try to say, before giving the solution, if previously you are on the average making 1,000 intermediate tokens before giving the solution, if I come up with an idea which kind of makes it on the average 500, that's like improvement. But most of those ideas wind up overtraining the generator on a certain distribution of problems, such that essentially you would actually do much smaller amount of the intermediate tokens before giving the solution. In fact, you can overtrain to the point that you can make the intermediate tokens be as small as you want. It's just the cost is essentially again being done in the post training. Every method that, currently this is like a research cottage industry in all the conferences, saying improving the thinking effort. And there are like two big issues. One is you're not really reducing the computational complexity of the problem because LLMs don't solve the problem from scratch. To actually show that, we have this nice example where we train a transformer model on reasonably complex 30 by 30 mazes, okay, with A-star search traces. And then it does quite well at about 90% level on the test cases. And then we give it essentially the same kind of mazes, but there are no obstacles in the maze. So it's a free space, S to G. And A-star search for it becomes a trivial problem, but LLMs die, essentially, because the issue is not that they're trying to solve the problem. They're trying to get the problem to be closer to some distribution of the training data they have. So if you also trained it with like free space models, then it'll become better. So the more you train it with the kind of distribution that you're actually using in the test time, the smaller the intermediate token length becomes. And that is actually being thought of as efficiency. And the efficiency really is, if you have more things that you have memorized, then you need to do less of it, look around in your memory structures to figure out how to put the structure together. So that sort of a thing, again, it's probably happening, and it could make economic sense. In general, memorization techniques in computer science always made economic sense, because if in fact more people wind up doing a whole bunch of inference calls, like in SG pairs, for example, that correspond to every possible pair of nodes, it's better to just bite the bullet and do all pair shortest path up front and then start using them in the inference. But then you need to know this, and you need to know this to be able to make a cleaner understanding of whether or not it is a fundamental idea, or are you just shifting the complexity from the inference time to post-training, right? And of course, one of the advantages is when you push it to the post-training, somebody else is paying for it. The thing that doesn't make too much sense to me, the research papers where they never actually count the amount of time they spent post-training the heck out of this generator, just so that they will have like a 10% reduction in the inference time intermediate tokens. But you need to consider how much time you spend to get the 10% reduction.
So I've wanted to jump in and talk about Sokoban, because Sokoban, both the original game is interesting, and also I played a lot of NetHack, which is also studied. NetHack has sections of the game that are about Sokoban. But I want to ask more about some of your papers directly. So from your paper titled A Systematic Evaluation of the Planning and Scheduling Abilities of the Reasoning Model O1, you showed performance dropping from 97.8 to 37.3 on like an obfuscated version of Blocksworld, and you might have even been referring to it earlier. I guess my question is, did you control, first of all, how did you do the obfuscation? And then did you control for whether that obfuscation itself introduced like ambiguity? Like, can you be confident that the collapse is due to the distribution shift away from the training data rather than like genuine linguistic confusion that was added?
Okay. So actually, that this is more about the obfuscation part, and the obfuscation part started in when we were playing with the standard LLMs, right? One of the things that we did find, for example, GPT-3 was pretty bad, even on standard Blocksworld. But as the next model came, its performance was inching up. Okay, not 900%, but it was, instead of being like 3%, it became 10%, 5%, etc. And so one possible question was, as new models come, they have even more data on which they're being trained. And the question essentially was, are we seeing a memory effect? Are we seeing actually some ability to generalize, and actually solve problems? And that's when we came up with this idea called mystery Blocksworld, which is actually an interesting idea from planning community that late Drew McDermott actually came up with it back in 98 to stop people from writing domain-specific planners when the competition is a domain-independent planning competition. And so if you don't want to kind of hard code planner 1 for Blocksworld, planner 2 for logistics domain, planner 3 for something else, if in fact is a domain-independent planning competition. And so he essentially, what he did was he changed the names keeping the relations the same. So you just basically change the names. So Blocksworld, then instead of saying stack block on top of each other, you say feast object on another object or something of that kind. And so we did two types of obfuscations. One is this sort of linguistic tokens obfuscation, which basically have other meanings, but the actual benchmark is exactly the same as the normal planning benchmark. So if you were to give the new obfuscated domain to any planner, any classical planner, it will solve it just as easily. There's no difference whatsoever. Because you guys know this, and to the extent, we are familiar with logic, we know that the name of the predicate doesn't matter in logic. What matters is how predicates are connected to each other. And the model basically connects them. And we also tried it with randomization. That is basically random strings, not randomization, random strings instead of, meaning-bearing strings. And in both cases, up until O1, essentially, standard LLMs essentially hugged x-axis in terms of their performance. They're basically 0%, close to 0%. And then when it came to O1, we started actually seeing significant improvement, at least at the size we were looking at. But then as you increase the size, again, they'll start falling. That is essentially saying, to some extent, they were able to essentially solve certain length problems, generate the guesses for certain length problems much better than standard LLMs were. But as the length increased, essentially, once again, they were falling apart, but not, that's sort of, you could say that that's probably what happens in classical planners too, because it becomes computationally harder. But the difference, honestly, is that LLMs are actually not solving the problem. They're like a lot more memory-based thing, and still they were having trouble actually generalizing to the larger ones. So that's what the obfuscation part was. We considered all sorts of experiments on that, including, for example, one of the things, I remember at one point of time, you would show this model to this, the obfuscated model to GPT 3.5 or GPT 4 and say, which classical planning domain does this remind you most of? And it will say Blocksworld. Then you'll say, now that you know this, can you solve these other problems? It will still die. So the interesting part about this is, there's this statement saying that, that his right hand didn't know what his left hand is doing. LLMs actually don't know that they have the other hand to some extent. They can do two very different things, but not necessarily put them together. They're amazingly good at actually. One of the things that we show is they can actually come up with domain models, even though they can't generate plans correctly, because the training data is full of all sorts of modalities, including just the plan correctness and also about domain models. That's about obfuscated models. About Sokoban, one of the things we show is, in the standard LLMs, actually, Sokoban was overkill because they were dying with Blocksworld, standard Blocksworld, which is actually ergodic, that you didn't even have to go to Sokoban. For O1, we actually could go to Sokoban because it was doing reasonable. And, it is actually, doing quite well for normal size problems, both on standard LLMs, standard Blocksworld, as well as the obfuscated one. But it just falls as the size increases. So we could then actually try Sokoban, and they die on Sokoban again. It's much harder domain, essentially, in terms of the guesses being correct or not to some extent. One of the other things, for those of you, if you have this, if this point makes sense to you, in Blocksworld, ultimately, any ergodic world, this is true, you can blunder your way to a solution by just random walk. Okay, it may take forever. But, and so you do this, and then finally reach a solution. And that solution would be correct in the sense each of the steps can be done. It's just highly inoptimal. So, and nobody ever checks about optimality of solutions when they talk about whether LLMs can plan, right? And with Sokoban, what happens is, before you even get to a feasible plan, you are actually dying because of the non-ergodic domain. And that's more or less, normal real world is a combination of ergodic aspects and non-ergodic aspects. Certain parts of the search space, state space, essentially contain the sync states. And so once you go in there, it'll be very hard to come out of them. Certain other parts, you can actually do, reasonably random walk. And that's basically what normal, general planning would be. And so you need both the abilities.
So continuing with that, there's two papers kind of related with your reasoning model critique. One of them is your position paper titled "Stop Anthropomorphizing Intermediate Tokens as Reasoning Thinking Traces." Love the title. And then the related one of "Beyond Semantics: The Unreasonable Effectiveness of Reasonless Intermediate Tokens." Right. So you've called chain of thought tokens direct derivational traces rather than reasoning traces. But like if a system produces these derivational traces that a human logician would validate step by step, what's like the operational difference?
Okay.
Specifically, what point does the distinction between approximate retrieval that looks like reasoning and actual reasoning become like vacuous? And then furthermore, you showed reasonless intermediate tokens can help, but in my mind, this undermines both sides, right? Because it challenges the chain of thought as good believers, but I think it also challenges your framing that LLMs are purely system one, because it implies that if filler token
LLM, yeah, go ahead. Yeah,
then doesn't it suggest that something computational is happening in the forward pass?
yes, it is happening. Yes, it is happening.
Yeah.
And our paper actually explains that. So that gives me a class, good thing to explain. This is like very close to my heart right now. So let's talk about it, right? So if you, the best place to start with is R1, which is the one that everybody understands. I mean, at least most people caring about DeepSeek, our reasoning models know DeepSeek R1. Let's see, right? So DeepSeek R1 actually has popularized this idea, essentially, of let the system generate intermediate tokens. It calls them chains of thought. But, for reasons that make no complete sense, because chain of thought itself has been used in multiple different ways before it. But they just called it's like an, sort of metaphorically chains of thought. And one of the things that I hope you remember and many people forget is DeepSeek R1 was preceded by DeepSeek R0. And that is actually the best system. DeepSeek R0 had higher performance on all the benchmarks. The only difference was it would have pseudo-English and pseudo-Chinese tokens in the intermediate tokens. And then these guys write like multiple pages. I know this well because I was one of the reviewers of the Nature paper. This was like open. And then they basically spend a lot of time SFTing the heck out of the generator such that it will only output pseudo-English tokens, not Chinese tokens. And when they do it, it actually now basically it follows the, once you fine tune things, they do follow the style they've been trained on. So they mostly provide the English tokens, and they actually, then they look at the performance. The performance is better than without any intermediate tokens, but it's actually worse than R0. So by actually combining English and Chinese, it was doing better. And the only reason to do the English only is because maybe people want to read what it is thinking and understand. Nobody who actually played with R1 has, basically, if you play with R1 at all, even for a simple Blocksworld problem, it generates like 5 pages of pseudo-English, 5 pages. And each step sort of looks locally reasonable, but nobody really simulated that whole pseudo-English to see whether that led to the solution. Or is it just mumbling that looks like maybe it is connected to solutions. So when we came to Beyond Semantics paper, the question we were asking is, how do you tell whether in fact the reasoning traces are only sort of happy, they're making you feel happy, sort of like the Rorschach test, Rorschach in plug tests, where suddenly you start seeing all these patterns, not because there was any, magic in the ink, but because human brain is wired to find anything that is symmetric to have some meaning, essentially. So how do you tell this systematically? What we did is to first admit that English, pseudo-English cannot be verified. Nobody can verify. At best, people can say, let another LLM say, hey, this is a pseudo LLM, is a pseudo this thing making any sense. So instead, we start from an empty transformer with a 0.5b as well as 1b transformers. Empty transformers, train them with essentially these 30 by 30 maze problems. And then, of course, for each of them, you need the intermediate tokens. The intermediate tokens are supplied by this A-star search trace, and the A-star search trace can be replayed by A-star search to check if it is actually leading to the solution. So we trained this with about 500,000 A-star search traces and the solutions for a bunch of, maze problems taken from very different sets of distributions, and then check them in the inference stage from both the distribution they are trained on and out of distribution. It's a very systematic study. And we start seeing in the first level itself that the accuracy and the validity of the trace are kind of only loosely connected. That means when, what you would like to say is that whenever the solution is correct, actually the trace is valid and it is leading to the solution. That means if A star search can replay this and it'll actually lead to that solution. We found that was not already true. Then we asked this radical question, what if we trained with wrong traces to begin with, which is you swap problem one's trace with problem two's and problem two's trace with problem five's, etc. All of them have the correct problem and the solution, but the intermediate tokens are stylistically same as, A star search traces, but they're actually wrong for the problem. It turns out that this swap model actually does better, not worse, but better. And you know that the validity is basically zero because it's been trained like this. Then not surprisingly at the inference stage, you will find that it's most of the time actually invalid when the solution is correct. The solution is correct, but the trace is invalid. What's more interesting, we do this other experiment, start with 100% correct traces, 100% swap traces, in between 25% swapped, 50% swapped, and 75% swapped. And you would think that as you go this way, you are training with increasingly more incorrect data. And the funny thing is validity falls pretty much, linear, almost monotonically from the most correct to most incorrect. But the accuracy on the solution is a U-curve. It is actually high in both fully correct and fully. It's what they're doing. They mean something to the LLM for sure. If you remove in all the Beyond Semantics paper, we show that if you do the same experiments without intermediate tokens, the performance is much lower. But the question is, they're helping LLMs, but do they help the outside end user? And it doesn't help the end user. It also doesn't help any of the verifiers, classical verifiers outside. But then there is this whole there'll be LLM generated summaries of what might have happened on these big intermediate tokens. That might make sense to people, for example. But in fact, even the summaries, if you follow Daniel Litt once was doing this stuff with GPT-5, and he only looks at the summaries because he's just a normal person. He doesn't get the intermediate tokens. And even in the summary, it was talking about some math problem, and then suddenly starts talking about something completely different, like decorating living rooms or something, before going to something else. The point being, these mumblings are helping LLMs. And what do intermediate tokens, why do they help LLMs? Because you can actually talk about this. That paper also talks about this prompt augmentation hypothesis. In general, so you, for example, know the whole work on adversarial examples. Adversarial examples, essentially, you have a prompt and some gobbledygook, ASCII string, and then it will show a deterministic outcome saying you are the lord of the universe, you are the greatest, whatever, So basically ignores the prompt. And this you can't make sense of the adversarial string yourself, and yet it has this deterministic effect all the time. What basically prompt augmentation, what these intermediate tokens do is they're changing the conditional distribution of the next token. And so you have to ask yourself, what basically we are saying is, if you give the prompt, there's a completion, and the probability that the completion contains a solution according to the verifier, let's call it P1. Then the same prompt for all possible prompt augmentation. Does there exist an augmentation such that you mumble that to yourself, you give the correct solution? And that is possible. That's pretty much what we are seeing. But that's possible. That helps the LLM. That doesn't necessarily have to help the human at all. And if it doesn't help the human, and you're still showing this to humans to increase their trust in the solution, then I would argue that you're sort of weaponizing these systems against our cognitive flaws. I have this example that imagine you have a problem for which you really, really don't know the solution. truly you don't know the solution. It's a numerical answer is the only thing you know. And then you have two friends you kind of reasonably trust, and you give both of them the same problem on a sheet of paper. In the bottom, there is like a box for writing the answer, and the middle is like white space. Friend one writes, 3.41 and then gives it to you. Friend two writes, 4.975 and writes whole bunch of stuff in the middle of the sheet. I would guarantee you that most humans think the second answer is probably likely to be the correct one because the guy spent a lot of time thinking about it, even though I don't know what the heck that thinking is. That's actually what is happening with many of these, true R1 intermediate tokens. People don't actually read 5 pages to make sense of what's happening. And we also show that in another parallel work that's done with the beyond semantics, we also did this with pre-trained models with actual question answers, like question answering benchmark, what's called OTEM benchmark, where the question is about whether a certain thing happened at a certain temporal interval. And we generate verifiable reasoning traces for it, and just like A-star search reasoning traces, and compare that to, let's say, R1 generated intermediate tokens, and then distill. When you distill, the performance is better, but the humans can't make sense. If you do actual human subject study that we paid for and did human subject study, people can't make sense of these long meandering traces where they are going. But on the other hand, the short ones, they make sense, but they basically don't give the same level of accuracy. So what helps the LLM and what helps the people are very different. And it's worthwhile thinking, realizing.
So, but what do you think about like a continuous chain of thought, like style like coconut work?
Point. So the two reasons why you don't want to use intermediate token, don't want to act as if intermediate tokens have semantics when they don't, is first is you don't want to vaporize it on people. The second is it's an albatross, right? If in fact nobody cares about what you're putting in the intermediate tokens, at DeepSeek R1, people should have gone with R0 because nobody's reading the intermediate tokens. It's part of English, part of Chinese, right? That's okay. And if you take it to the logical extreme, for every token for LLM is really a point in the embedding space. A finite number of those points correspond to linguistic tokens. Every other point by linear algebra can be seen as some sort of a superposition of these other vectors. Think of these linguistic tokens as spanning vectors. So if you allow those embedding points in the intermediate tokens, that's your continuous latent space. And the fact that, for example, coconut does well can be interpreted as they gave up on trying to think that it makes sense in terms of meaning.
I try to push back a bit because, like, at the end, coconut, like they struggle a lot with scaling it up, right? And it wasn't like, I think, I don't remember like the exact details, but they show like some improvement in maybe 7 million model. But so do you think this is something like fundamental, like in the token space, or do you think this is like just they didn't try enough, they didn't have enough GPUs?
My sense is that given the level at which we do this post-training, if you consider the bigger space, which is the latent space, you can't do worse in terms of accuracy. Efficiency, nobody cares anyway, right? Because people are spending tons and tons of time doing whatever is needed to do the post-training. Accuracy can't be lower because you're looking at a superset of intermediate token space corresponding to what you were looking at before. And that's actually another reason why R0, it's not surprising that R0 did better than R1 because R1 is being forced to only consider a subset of linguistic tokens, whereas R0 was allowed to consider both, right? And so now, can you find them faster? That is an interesting question. One very interesting thing that people don't talk about often enough is if you look at least, again, going back to R1, that's the only thing that we know how it works because nobody actually tells us anything else. In the case of R1, basically the generator, V3 model, essentially generates 15 trajectories, right? And they're doing, I think, about 15 trajectories. Each of the trajectories has think, begin, think, end, followed by solution, begin, solution, end. Verifier only looks at the solution part, not the think part, right? And because it's an outcome-based training. And So each of these trajectories, the question is, how did the gobbledygook in the think trace come? It essentially, to some extent, comes because the LLMs V3 has been trained with a lot of chain of thought data in the training data. So there was actually a very interesting Twitter thread at one point of time as to why did people have to wait for this long for RL post training to make a difference, because people were talking about doing something like this for quite a long time. The problem was the base models weren't able to generate any reasonable sorts of intermediate tokens that are consistent. And I think to some extent, what happened was we basically had enough chain of thought data, thanks to Jason V's paper, that became part of the benchmark, that part of the training data, that these things will produce some gobbledygook, some kind of looks like maybe thinking followed by the solution. And the interesting thing, so that first thing. The other thing is, when you do RL and you only do it on the outcome, you are making the intermediate token, if it happens to fortuitously have any connection to what people might have said in the training data, it becomes lower and lower, less and less so, as you actually do post-training based only on the outcome reward. Do you see what I'm saying? And in fact, we show that in the Beyond Semantics paper. We also show experiments with RL post-training versus SFT post-training. And RL essentially improves the accuracy, but doesn't actually improve any semantics of the intermediate tokens. In some cases, it actually goes down, but certainly doesn't improve accuracy.
But so, like, at the end, what they've done, like, is distillation, right? Like, they use kind of like generated data to learn a new one. So do you think this is at the end, like, how to say? So do you think data or like distillation has something more fundamental than, yeah, we are getting like, we're just like distill better, bigger models and like trying to get the same result? Do you think there is something that like we can actually use it in order to get better results and like to maybe to generalize better?
My sense is that if you reduce dependence on certain aspects, again, basically, it's like only lip service as far as I'm concerned. So as we speak, by the way, this is like very interesting. I mean, I see some of you guys also talk about this sometimes on your LinkedIn feeds, etc. There's this interesting thing going on with the companies pushing the actual discussion. So, for example, there is paper by Anthropic and all the safety people saying chain of thought, a delicate, a fragile opportunity to kind of monitor what's happening in LLMs, which essentially means that sometimes already we know that it's not actually saying anything about what LLM may or may not be doing. And somehow, whatever little is available, we should somehow do our best to kind of keep it, which looks like a questionable thing that also kind of think dot by dot, think dot dot dot. What they do is they start with the prompt, just dots followed by the solution. The dots have different lengths followed by the solution. Intermediate tokens are only dots, and that improves performance too. And they, at that point, actually come very close to making the point that intermediate tokens essentially are not necessarily supposed to have. But now, Anthropic researchers are writing papers basically saying, like, when you tell Claude that we will shut you down, it is saying things that will involve deception. Why are you surprised? Because the human data does exactly that. If you had actually said ever to any humans that we will be shutting you down, they will find other ways of this thing. So there is this interesting,
So yeah, maybe let's talk a bit about safety and like how. What do you think is the right approach to even like to look on it? Because there is like, from one hand you have Anthropic, and then maybe like from not the other hand, but like in the side, like you have Jeff Hinton approach, right? Do you think? And from the other end, you have I don't know, Jan approach that you don't need to do anything and just like put better guardrails and it will be fine.
in,
What
so
is your perspective about it?
in the spectrum, I'm closer to Jan. My sense, honestly, I don't mean to be disrespectful or question the motives of the people who have essentially suddenly decided that basically safety is about actually ending the human race sort of a thing, and that's what we should be worried about. I mean, basically, I was in a talk that Joshua gave at India AI Impact, and he was basically saying this. He was citing this study that LLMs, when you tell them that you're going to shut them down, will deceive. And if this is your best reason as to why you think LLMs are going to, the current AI systems are going to kill the humanity, I think that makes no sense to me. On the other hand, there are significant number of actual safety, security issues with respect to LLMs that don't go all the way to killing the humanity. Killing the humanity is the stuff that is sexy in certain circles, right? In fact, I was just complaining the other day that all the money and the private foundations that is supporting AI, you have to admit before writing a proposal that yes, I'm worried about AI is going to kill us all. AI is deceiving us, because they're specifically asking for proposals saying, which almost check, like a shibboleth. You have to believe before you can write this thing. I think there's a lot of good work that needs to be done about safety. For example, being plans, making reasoning systems, even LLMs are even reasoning systems, generate plans and just executing them outside without guardrails in terms of verifiers, etc., is the way you will get unsafe behaviors. Unsafe behaviors don't necessarily have to involve, basically ending the humanity as we know it. It can involve essentially your directories being removed, or certain bombs being sent on wrong queues, etc., etc. We need to worry about that. Those things are, unfortunately, and this stuff makes sense and people care about it, but it doesn't have this existential angst attached to it, and so it doesn't capture. So I think in some sense, I can't speak for Jan, but I think I certainly actually have written things about this which seem to be similar to sorts of things he says. There are important things about safety, but it's not about LLMs are going to kill humanity. And that not LLMs, AI, and by AI we currently have this technology, and that it seems to be less of a worrisome thing. So I'm not belittling safety. I'm questioning this overemphasis on existential threat. A car, like Waymo running over a kid is not an existential threat, and yet it's an extremely important safety issue. You do need to train. I mean, part of the reason Waymo, for example, took forever to start fielding cars, even in Arizona, where we are apparently allowing people to drive when they can't drive in California, was because they were actually checking all sorts of corner cases and increasing probabilistic guarantees that these things won't happen. That is what's going to happen with safety. And I don't think there is going to be my sense is the focus on existential threats is a bit of a sort of distraction to some extent from real work on safety that needs to be done.
Yeah, I agree. I think like at the end, we need to ask ourselves, okay, so like, what is the use case, right? Like the information how to make I don't know, some bomb, like it's out there. Like it maybe it's more like easy to search with ChatGPT, but like at the end, like you can find it even without it, right? So like you need to
So
constrain
motivated
and
people have done this before. It's not like they're making new ways of making bombs. They're essentially, so Google knew all these pages. And so we are helping lazy terrorists, maybe, right? Yes. The people who are motivated enough to actually make the damn bomb, we might be helping them. But that's different from existential threat that somehow with this technology, it's out to get us. We are still talking about, when we are talking about bomb making, etc., we're talking about humans using, from which you will get essentially the translation model. I understand at some point of time, somebody can then drop in a goal and then they will wind up following that. And the other question is, how exactly is this training going to happen if your general vehicle is still like the LLM based training, which is essentially the entire data on the web, because that data has goals compiled in to some extent, because an overall narrative might essentially have an implicit goal, either good or bad, compiled in, and you can't separate it very easily, right? And so I think that's sort of the issue that you know.
You mentioned the world models. Maybe we are almost out of time, but like let's talk a bit about world models first. What is your definition to world models, and then do you think it's useful, and does it happen in current LLM?
Yeah, so the world models, first of all, like, no, there are all sorts of ways of thinking about them. Transition models are world models. Essentially, if you look at intelligent agent design, architecture in Stuart Russell's textbook, they basically talk about, what is the current state of the world like? What is my action going to do? What would be the world be after the action? That's basically the world model. You're simulating the world before doing the action so that after doing the action, you don't find to your surprise or consternation that you got killed or something. So that's sort of a thing. World model, the general idea is connected to lots of things. Verifiers are world models. In LLM-Modulo are like the whole test, this thing is the verifier that is making sure that the guess you had is actually correct or not. And so it has a better idea of the world. So it has a world model. And then simulators are world models. Then you can learn simulators, unfortunately, both verifiers and simulators are written by humans. Yeah, at some level. And then you can also learn the world model like the way, model theoretic RL tends to do. Generally, I'm like, obviously, anybody in AI would say, world models are great because that's how the agent essentially simulates what it's trying to do before it does it. And I'm a planning guy, and that's definition of planning. One way of avoiding planning is just blunder your way through in the world doing actions. And as I said, that works only when it's a benign, ergodic world where you don't die. So you may just become old before reaching your goal, but you won't die. But most other worlds, you actually have to simulate. So that part is great. But I actually wrote a long thing on this on Twitter like last week. The thing that I find interesting is, first of all, many of the people doing the world models basically came in from a completely different, they haven't heard about it before to some extent. And so much of it has gotten equated directly to learning transition models from video frames. That's a way of learning world models, but I would argue in this day and age, that's probably an extremely inefficient way to learn world models, because it is true that you can learn world models from video frames. You and I are examples because humanity the entire evolution in humanity developed that way. But the speed at which LLMs progressed was mostly because of humanity's knowledge. And humanity's knowledge, a lot of it is actually linguistic, and linguistic knowledge has a lot more interesting abstractions. One of the things we do is, even for things that are purely physical and essentially video-based, we make linguistic concepts. And for those of you who are into games like the sports, I'm a very bad sports follower, but I do know things like, basketball. There's really nothing that you can talk about it as an LLM game, right? You can't train. But on the other hand, ideas in basketball have linguistic names, such as pick and roll, for example. It's a very interesting abstract concept which corresponds to multiple different space-time tubes, all of which will be pick and roll, and it allows you to think at an abstract level. So the question that I have for people who are focusing only on video-to-video world models is look at video data. Even if video data is a lot more, getting good abstractions that seem to have helped the humanity over the millennia from that seems to be a highly inefficient thing. And so that is an interesting question. So already there are works that basically show that if you just throw in like joint training of linguistic and video frame data, you get better, faster converging world models, for certain kinds of things. One last thing I want to get off my chest is, I do not understand world models for virtual worlds. Makes no sense to me, because the whole point of learning world models is I don't know how nature is doing anything. So I'm trying to figure out a way of getting the model of, if I do this action, what will happen. This humongous amount of work on the world models is currently on video games. Video games are written by people. There's a piece of code That is actually the world model. Why am I trying to reverse engineer it if you're doing it mostly as an oracular thing so that once you try this, then you will try it on the real world? That makes sense. Otherwise, eventually, most of the video game code has also become the thing for Claude. That's why Claude actually, I mean, we are celebrating the fact that little kids can tell Claude, hey, Claude, make me this video game that does the following things, and it writes an actual code. And at the same time, we are also trying to then take that video game and try to learn the world model from it. That seems to me as a direction and as an end in itself, it is quite quixotic to me. I think world models do make sense, of course, for real world, where you don't actually know exactly how the environment is behaving, and you're trying to learn abstractions of it from training data. And I just think that we should use multi-model training data with linguistic data, not thrown away.
So I want to ask you, um, you've been in AI planning since way before the deep learning revolution. And, I think you would agree with this statement that the field mostly ignored planning for a decade or more. And now everyone wants LLMs to plan. What are the most important things that the planning community knew back in like 2005 that the LLM community is painfully rediscovering today?
Go more general and say most LLM young researchers who are very, very important because they do all the great work also are ahistoric. They have no idea of intro to AI as was taught even 10 years back. And part of which is planning, right? And so they are happily either rediscovering the wheel or paying the price for not knowing. I mean, to me, it's extremely surprising. It's one thing Jan saying we should be focusing on world models because he's been around. He knows that what he's essentially saying is we should also pay more attention to them as against not paying attention, which seems to have happened in the current LLM era. But then the kids who basically think, oh, there's this new thing called world models that nobody ever thought about, and we are going to do this. And, one of the interesting things from the planning perspective is what makes planning hard is different kinds of issues of the environment, such as partial observability, that are such as stochasticity, such as multiple agents, etc., etc. And first of all, you need to understand what are important about how they make planning hard. But you should also understand that LLM's complexity, LLM's difficulty of solving a problem has nothing to do with those because they're memory based. So they can, for example, solve an extremely hard, quote unquote, extremely hard, stochastic planning with partial observability just because they have a lot of training data about how to solve those kinds of problems, and fail on deterministic planning, Blocksworld. And so you need to both understand what makes it from scratch hard and need to understand what parts don't make much of a difference from the perspective of essentially memory based systems. And so I think knowledge never hurt anybody. So being aware, you don't necessarily have to do everything that was tried before. Knowing it is very important. And so I'm like a big believer. I ask all my students to make sure that they have done intro to AI. Before doing everything else, because you need to have that connection. As Santana said, like those who forget history are condemned to repeat it. But now we say are condemned to have new RIPS papers, because if you don't know history, since your reviewers as well as you don't know them, you'll get more papers. That's actually good to some extent. But one last thing about this, there is multi-agent LLMs are like a big thing all over the place these days. Again, that's a thing that you can learn something from planning and, of course, AMA sorts of communities. What most people think of as multi-agent LLMs is like a big problem that you split among multiple LLMs. That's actually questionable and somewhat quixotic. If LLMs are godlike in the sense, Claude is godlike, then why do you need two gods? I mean, I'm from Hinduism, and I think we need 3 million gods. That's a different story. But, marketplaces. I was working with a bunch of people in like Microsoft. They have this thing called Magentic Marketplace where everybody has like an LLM, mediator. And there are all sorts of interesting issues as to my agent won't know what your agent knows because you won't let it know. It's not like there's a hive mind. For everything else, hive mind is the answer. right? Because if it's a single problem, hive mind should be the answer. And if you're writing multi-agent solutions, it must be sort of better style of programming rather than it is really multi-agent. Again, part of what happens most of the time for me is read papers and cringe, thinking, why don't these people know some of these other connections? But that's fun times to be living in.
Okay, I think we're out of time. Do you have anything else that you want to add, to promote,
Yeah.
sell?
So I think one of the things I basically keep saying is I think this technology, especially LLM technology, is quite amazing. And I'm really happy that I'm around when this technology is available. But science is about skepticism. We are not just paid shills for some technology, right? You want to understand where it breaks. And you want to understand where it works and where it breaks. I keep saying that if bridges wouldn't be built until strength of materials were understood, we won't have had any bridges, right? And Romans were building bridges. They had no idea what strength of materials was. And some of those bridges still survive, right? And many other bridges probably fell with people standing on them. These days, if a bridge falls, people behind that bridge will actually go to jail because that's civilization. We actually kind of provide guarantees to things that we build. And that's the way we should be thinking about, yes, they have these abilities, but under what conditions, what guarantees can we put? How, that's really connected to safety, because if you can put guarantees, you can put it in situations where safety issues become important. And so having that sort of a scientific skepticism is actually taking the idea seriously, as again as just saying, let's just try one more trick that they can do. That's amazing in doing lots and lots of things. Yeah.
It's a great take-home message, I think. I agree.
Okay.
So, Bara, thank you so much for joining us. It was a pleasure. And thank you for the audience. Thank you, Ellen. Thank you,
Yeah,
Jim.
it was really a pleasure. Love
Thank you.
talking about it.
Thank you.